Good afternoon, and thank you for coming to my talk. You've had 4.5 days of amazing talks. Now, I also had 4.5 days of amazing talks with amazing slides, and the good thing about it, I can steal the best bits from the best slides of the best talks. The downside is you've heard 4.5 days of amazing talks, and now you're here. So we're going to talk about designing software for performance where like maximum performance is a goal. I have to give you the context, who I am, what I do, why we're doing this. I work for the company called Mentor Graphics that is now part of Siemens. What we do is electronic design automation tools. These are the tools that I use to design and manufacture pretty much every integrated circuit that you can buy now. So if you have cell phones, both like Apple or Android cell phones, if you have PCs and laptops, if you have video cards, and down from there to microcontrollers, our tools were used to build, test, model, and manufacture those circuits. Performance is often the most critical feature. Tens of millions of dollars can ride on outcome of the benchmarks. So it is, I was joking, but it could be more important than correctness. I've had the request many times, okay, we want this feature. Well, your feature doesn't always work. It doesn't work if this or this or this happens. That'll never happen. Our chips don't do that. So, we run it on 3 chips, it works, do it. I've never had the same thing about performance. Yeah, it seems good enough for now, but what if something happens, something we can't even anticipate, but we still want to guarantee that it'll still run overnight? So that's how important performance is to our customers. Now, for them, it's also tens or hundreds of millions of dollars riding on their throughput. So, I make jokes about it, but they're not stupid. They're driven very hard by their own business requirements. So, under all this pressure, how well did we do as an EDA, business overall? So, this is some EDA tool. I picked a specific one, doesn't matter what it does. So we're running on some chip on the same hardware, and I'm running the versions from 2010 and all the way until today, and this is how many hours it takes for it to complete that job. So we've done pretty well improving our software over the years. But that graph is completely irrelevant. And why is that completely irrelevant? Because once the integrated circuit has been designed, modeled, and produced, nobody cares. When it goes into manufacturing, you buy it. When people who sell it care, but nobody else. What matters is how long it takes for us to operate on the latest design that is about to go out using the silicon for computing that is the previous latest design that just came out. We run on the latest versions of the CPU, manufacturing and simulating the next latest version of the CPU, and we do it every time. And the answer works out to something like this. So we're more or less constant, we're barely keeping up with the growth of the problem, but even that's not entire truth, because now I have to show you the number of CPUs. We're barely keeping up at the cost of constantly increasing the compute power that we throw at the problem. And now that starts to look really bad, like we're doing a totally crappy job. And that's also not the whole truth, because what I didn't show you is, okay, what goes into that latest design. The transistor count is roughly proportional to the size of pretty much anything you're going to do in this design, whether it's a simulation or manufacturing or verification. So that's exponential, it's a logarithmic axis. But it gets worse than that. These, and again, it's a logarithmic axis, these are the number of they call them the number of rules. Think of each rule as an independent operation. So if it was a C++ program, it would be the number of statements in your C++ program where each statement is approximately the same computational cost. So this is the size of your C++ program. The previous slide was the volume of data the program runs in. It's logarithmic axis in both cases. So both the size of the program that we have to execute grows, the amount of data it runs on grows, the number of CPUs we throw at it grows, and overall we're managing to hold our own. Now that's the performance side. Now the product side. Our company has been around since, well, I didn't find the press release of 1995, which this particular product was introduced. So 96 was the first press release that I found. Actually, product starts from 95. We still have some of the code that was written in the 90s. There are a lot of new components, a lot of new tools, a lot of course, technology evolved. We have a lot of new physics thrown in. We have a lot of new operations thrown in. But some of the components actually have the same design as they did back then. So for us, software design means survival. If you have a crisis today, you can hack your way around it. And if you keep doing that, you accumulate a technical debt that you will have to pay off. And you can either pay off as a sort of continuous drag on your operations. Everything becomes more difficult. Everything becomes more expensive. Or you can pay it off by investing time into rewriting a piece of your software entirely. Unfortunately, this requires that you basically dive underwaters for 6 months. When you come back, there may not be a market for you anymore. So design is a foundation of a software. A good foundation lasts, allows you to build designs that stand the test of time, are adaptable to changes, including the changes that you didn't expect when you build the foundation, but you kind of anticipated what kind of things we might want to change. And we do have some of those. Some of our stuff architecture is 10, 15 years old, and we didn't have to change it. We added a lot of code. Some of it we replaced all of the original code, but the components, the modules, the data flows still are the same. Design truly is the foundation of the software. I didn't say it's the foundation of a good software. It has to be adaptable to changes. I didn't say that it has to adapt in any organized fashion. And just because the architecture is the same after 10 or 15 years, it doesn't mean that you would want it to stay the same in the ideal conditions. Unfortunately, it's difficult to justify the rewrite. Well, you all know the stories about what would happen if software was like cars or like planes or like houses. Software isn't like houses. And why isn't software like houses? In the context of what I just said, because unlike houses, you actually can build software without any foundation at all. And you get to a point where nobody can change anything, and your best hope is someday it'll just die. Now, we do have a lot of good design practices, and we can talk a lot about them, and we did in other talks. So in the context of performance, do modularization, separation of concern, do all of those things, good interfaces, do they help write the fast code? And in my experience, the answer works out to be kind of. They do make it easier to improve implementation, and that's their intent. But for pretty much every good design practice, I have seen a design that was either efficient or could be made efficient with the help of that good design practice. And I have seen a design where it was good, it was beautiful, it was well done, but that architecture aggressively resisted attempts to optimize it. It was poor performing, and it couldn't be easily made better. So it's not enough just to have the good design and optimize it. You have to build performance as a consideration into your design from the very beginning, along with things like modularization and so on. Performance has to be one of the initial objectives, because otherwise all the other good design practices don't guarantee good outcomes. So how do you design for high performance? I could tell you, but it's the wrong question to ask at this point in the talk. And the right question we should be asking is how not to put you all to sleep. And now I'm going to steal a slide from Titus. Well, the idea of the slide anyway. You can approach designs in a descriptive manner or prescriptive. Do this or tell a story. And Herb can come out and read from the guideline list in a purely descriptive manner and hold the audience on edge for 1 hour. And I can't do that. So I'm going to be descriptive and tell you stories, with thanks to Titus. So what we're going to do, we're going to dive into some code and run it and try to make it faster and benchmark it and so on. And it's kind of like diving into the huge dumpster behind fries. Lots of cool stuff in there, and maybe occasionally you come up for air and you have a real gem in your hands. So that's what we're kind of trying to do. So how would diving into a particular chunk of code help you with the design? If you have an old design and you want to improve performance, all you have is a lot of code. Where do you start working with performance? Now, we're talking about designing for performance, so we have the new design. Well, your new design will be an old design someday. So you have to think about how are you going to improve its performance. And to improve its performance, you have to know something about performance. And performance knowledge has to be gained through measurements. There is a fundamental difference between designing for performance and other practices. I can show you some design ideas. We designed the code like this, our system like this, and then we could write code that looks like this. And you would all go, ew. But you can't do that with performance. You have to measure. Our intuition on performance is notoriously bad. There are a lot of things that could limit performance, memory access, CPU access, lots and lots of other things, concurrency. And it's not always clear even how to distinguish, how to define it. Well, I'm actually going to try to show you that, but you have a disk-bound program, but if you're storing compressed data, you could be actually bound by the speed of compression, not the speed of writes. Lots of situations where you can trade one limitation for another. So let's get behind our local fries and dive into some code. So the most simple example of code, with one exception, I'm going to show you kind of distilled examples that try to capture the essential bits of real designs that I worked on, but they're sanitized so they can fit on one slide, and hopefully they still capture the key ideas. This is straight from the textbook. This is how matrix vector product is defined. If you just look at the math textbook and just code it up, convert all the arithmetic operations. And this is done on arrays, so at the lowest level, and I'm not doing it because I advocate, working with arrays instead of vectors. I'm just doing it to make sure, there is no distractions. We don't ask the questions, so what happens here, what happens here? It's just memory and computations. Nothing else is happening here. Oh, I guess I have it opened already. Okay, here it is. That's the same code, and I'm going to benchmark it, and I'm going to use Google Benchmark. So I'll show the benchmarking once, and I'll never show it again. So I'm going to manufacture some random matrix. That part is not measured, and this is the benchmark routine. So all the Google benchmark routines are freestanding functions. They take this benchmark state. If you don't know how to use it, just go to the Google benchmark page. It's very simple. They have examples. This is the relevant part. It will decide how long it wants to run benchmark based on the statistics it accumulates. So while it wants to run, it will call this matrix vector product function and measure how long it takes. And it does some averaging and accumulation and statistics, and then it decides, okay, I've got good enough average, I'm done. And then it'll print how long it took and how many items it processed and so on. And you can do it for different sizes of the matrix. So here is, I'm going to do 3 different sizes of the matrix. So again, this is the code I'm benchmarking. Okay, let's run. Yeah, probably should have shown you the compilation. GCC 6 on this machine. C++ 14 vectorization enabled for AVX2, which is actually the native platform. It's running on this laptop, the native platform. So pretty much regardless of the size of the matrix, 256 by 256 or up to 1024 by 1024, it runs at a speed of about 800 million elements in floats per second, and which boils down to a reading memory just at about 3 gigabytes per second. And that doesn't really depend on how much memory you have, at least in this case. So going back to this code, what can we do to make it faster? Yes? Okay, so somebody said remove the reference to float. I would hope that the compiler would optimize it away, but we can actually look in and see if it did. Okay, so maybe remove the reference. What else can we do to make it faster? Okay, somebody said parallelize, and there are two ways to parallelize it. You can ask the compiler to do it. Now, there are two ways to parallelize. There's threading and there is vectorization. Which one did you mean?
I meant threading.
Okay, we can do it on threads, and that's, so I actually tossed out the entire design for concurrency chunk out of this talk because it didn't fit in, gives me the idea for the talk to give next year. So yes, it's fairly easy to parallelize, but it's also possible to do data parallelization, which is the vectorization. And we can ask the compiler to do it, or we can do it ourselves. And I don't have the time to go through all the steps of getting the compiler to do it. It's possible. It gets you about 2/3 of the way to what you can do yourself by hand, and that's the limit. You know, it's another interesting talk on getting your compiler to vectorize the best. It's another hour, unfortunately. I don't have time to do it. So, let's see. Before we ask actually how can we parallelize this, one important question to ask here is, why isn't it faster than it is? What's limited? Is it limited by reading the matrix from memory, or is it limited by the multiplication operations and the additions? Okay, by applause and other signs of being awake, please, who thinks that it's limited by computes, basically by multiplies and adds? Okay, thank you. Now, who thinks that it's limited by memory reading? All right. Okay, and there is only one way to find out. We're going to profile it. Okay, same benchmark run on the profiler. Going to look at the profile report. I'm going to do this only once. Every other time I'm going to tell you what the results were, but you can come after the talk and verify, that everything I told you is true. When it comes to performance, don't believe anyone, verify everything. So we're actually going into disassembly, and okay, the profiler actually doesn't give us the answer. It kind of tells that both of you were correct, because there are 3 instructions that takes the longest time. The top one is a multiplication. It's partially vectorized code. If you don't know these instructions codes, they are like SSE instruction codes from one of the SSE families. So the top one is a multiplication. The second one, the one that is 49%, is addition, and the bottom one, the vmove_ss, is store, or it's a load. It's either store or load. Well, this one is a load. So the profiler actually tells us that kind of all 3 are to blame. Multiplication takes actually less than half. Addition takes longer, and store and reads are non-trivial. Now, what you have to know about these profilers is their attribution to a particular instruction is questionable. They can attribute pretty accurately to the place in the code, but not exactly down to one instruction. If they say this one instruction, it could be the one before and the one after, and that's if it's a good profiler. They aren't that accurate. It's just the way the hardware counters work. There isn't that precise of a measurement tool in the processor. So that really didn't give us the answer. You were kind of split on the memory versus computes. And we are still, the profiler gives us a wishy-washy answer, but taking into account also what we know about its inaccuracy, we're still split. Well, we can actually do the other experiment. We can take out the compute and just benchmark the memory access. So here is some memory read. I'm just reading from memory, syncing into some variable. I made it volatile so the compiler doesn't do anything fancy. I put a macro that repeats that line 32 times to reduce the overhead of the loop. Yeah, the benchmark loop is highly optimal, but not that optimal when you're benchmarking one read. So it changes the result slightly. And I'm going to benchmark reads and writes. This code is not critical for what I'm talking about, so if you're curious, just come back after the talk. We'll go through every line of code. The point is, I'm going to now find out the actual speed of reading and writing the memory. And remember, the old benchmark is still on screen. 3-point-something gigabytes of memory per second, that's how fast I was processing it with the matrix vector product. These are the raw reads, the same sizes. I can read memory at a rate of about almost 20 gigabytes per second, and matrix vector multiplication is mostly reads. And I can write small amounts of memory, and I'm only writing that vector out, at a speed of about 12 gigabytes per second. So my matrix vector product, if it didn't have any compute, could be running at basically at 18, 19 gigabytes per second, and it isn't. So it's clearly compute bound. Which means we have to focus on computing, and that's where one of the ways we could do is vectorize. Okay, I'm going to jump all the way to the end, and I'm going to show you the vectorized version, the one that is vectorized by hand. This is done in the GCC intrinsics. I could do it in inline assembly. Looks rather similar. They have pretty similar names. There is in AVX a vectorized instruction, which is a scalar product. That's exactly what we want. Because matrix vector product is a scalar product of a vector that is a row of the matrix times the vector that you're multiplying. Each element is a scalar product of two vectors. So they have an instruction that does a scalar product, and it does them 8 at a time. So not the whole vector at once, you have to call it multiple times, but it does scalar product on vectors of length 8. Then we go to the next 8 and so on. We have that, so we can do the scalar product of length 8. And how do we express our matrix vector product? Well, we now put it in a loop and we jump in increments of 8, and we accumulate the result. That's all. Let's see. Okay, this is our product of length 8. This is the scalar product. I create an extra function, just does that, just the scalar product of arbitrary length. I'm assuming that the length is divisible by 8, so I'm not dealing, for the purpose of benchmark, I'm not dealing with the branch. If you actually needed to do it in a real code, you would do a check up front. So you wouldn't put an if inside, you would do a check up front, carve out the piece divisible by 8, and handle the rest separately. So here is my matrix vector product, and I'm going to run it. Didn't see that one coming, did you? What happened? Okay, did somebody say alignment? Okay. That's right. The x86 vectorized instructions have specific alignment requirements. That particular one is a 32-byte alignment. Now it's actually time to get out of the dumpster and look at what we found. Here is an interesting design consideration. Well, first of all, we actually learned something which we kind of skipped over, but now that we're taking a pause, the vectorized instructions do 8 elements at a time. Imagine if we implemented our matrix vector product with an interface like pushback, where you're showing one matrix element at a time and accumulating the matrix vector product. With that interface, you wouldn't be able to do this unless you accumulate it and you went to an explicit finalizer, which is to say, I promise I'm done. And until you call that finalizer, you're not done, so you're in an undefined state. The explicitly finalized implementations are possible, but they're kind of ew. So an interesting design consideration here. For the purposes of performance, prefer a high granularity API because it gives you more freedom to optimize the implementation if the implementation knows more about what you're ultimately trying to do. Take one element of the matrix, multiply it by one element with this one float over here, and give me the answer. Well, I don't know much about where you're ultimately going. Take the whole row, multiply it by this whole row. Now I know a lot about what you want. Well, that's one, but the thing we just learned with the crash is we suddenly need a memory alignment. We didn't need it before, so now we do. Depending on how the whole memory management system in our design was designed, that could be a very disruptive change if we didn't think about it. In our case, it's easy. We'll just do aligned memory allocation. I just switched malloc to POSIX memalign. Okay, this is the fully vectorized one, and I'm actually going to show, there is another optimization that I'm not going to explain. You can switch to different loads that bypass caches. And again, it's a talk about vectorization. The compiler never does that one, by the way, just never. At least not anyone that I know. We're now reading memory at the rate of 20 gigabytes, 24 gigabytes per second, which actually slightly exceeds the benchmark which we did for the maximum possible speed of reading memory on this system. So first of all, we appear to be memory bound, but we actually appear to be like over bound. How did that happen? Any ideas?
Vectorized memory load.
Yes. We actually, our original benchmark is invalid because in the process of doing that, we kind of silently switched on the fly to reading, instead of one float at a time, reading the whole 256 bit at a time. Well, no big deal. We can read 256 bits using the 256 bit read instruction. So now we're going to find out what's the real memory bottleneck on this machine is. Okay, so we're still compute bound. So now here is a more philosophical question. That gain in speed from 3 gigabytes per second in multiplications to 24, did it come because we read the memory better or because we multiply better? You really can't tell the difference. I mean, it's very hard to take them apart. The same instruction does both. Now, one thing is, again, this was what we had to do, and the streaming loads were even worse. You really don't want to see that code all over your design, trust me. So, on the other hand, if you write high-performance code, you do have to deal with very low-level code, sometimes non-portable code. Sometimes you have to abuse the language to coerce the system to do something fast. How do you reconcile it with good design practices? You contain it. A good design would encapsulate, contain, isolate this kind of badly written but very efficient code. Take care when you design the APIs and abstractions for this, because they will limit what you can and cannot do with this. If your API says, we're going to process 8 words at a time, and that's enshrined in your API, now you're stuck. You can't use 512-bit operations. So you have to be careful here, but you have to encapsulate it. We have also learned that in memory access speed is kind of important. We were bottlenecked by memory, and we definitely, at least part of the reason we're so much faster is because we're reading memory faster. I don't know how much, but we actually are multiplying faster than our original non-vectorized code could read. So we definitely went over the original bottleneck for reading memory. At least that much happened. Because if we were still reading memory at 19 gigabytes per second, we wouldn't be able to multiply at 24. So we got at least somehow over that memory barrier. We should pay more attention to memory access speed. Fortunately, it's easy to measure. This is basically the same code. It now only does the memory write. So let's see. Oh, here we go. Okay. Oh, the bottom part. Okay, I'm going to do an indexed memory writes this time. So I'm not necessarily scanning the entire array in sequence. I'm going to do indexed writes. And reads are the same way. I'm just going to do writes just for brevity. Reads are the same way. I have an array, but I also have a secondary array with indices. And those indices could be consecutive or random. And I'm going to measure indexed reads where my indices are consecutive. So if I'm doing consecutive indices, why didn't I simply do consecutive reads? Why didn't I do consecutive reads? Huh? Sorry? Yeah. Well, that's one, but I did it to be fair to the benchmark, because the random benchmark has no choice but get the indices out of the index array, and that also takes some time. So I want to do the same operations. You know, it wouldn't be fair to compare indexed read with a non-indexed read. So I'm doing indexed reads both ways, but in one case my indexes are sorted, and in the other case they're random. Wrong screen. Oh. Okay, so writes, reads would be exactly the same. So depending on the size of the memory, sequential writes start at about 10 gigabytes per second. Again, this is all running on this thing over here. Drops down to just under 7. These are random writes. Again, starts at 10. Ooh, now that's going to hurt. We're now down to, oh, we're below 1. We're below half a gigabyte, and it's still going down. I'm going to show you the same thing. This is the graph of what you just seen. Sequential reads, sequential writes, 10 gigabytes per second, slightly dropping within this memory range. It'll go down a bit more if you write more, but I didn't want to start paging on this laptop. Random writes goes down, and then more down, and then some more down. Well, okay, that looks kind of interesting. What can we learn from this about designing our software? A lot of designing your software is about designing your data structure. So more generally, data structures you could change. Designing your data organization, that goes into the design, how the data is organized. And it goes into the design because it limits and determines the ways you could access the data. And that in turn limits which algorithms you can use. So going back to my matrix, if I had 1 million floats and I wanted to store them in a contiguous array, they would take, they're 4 bytes each, so they would take 4 megabytes, and scanning that array, writing it once, sequentially would be going at a speed of almost 10 gigabytes per second. If I put the same floats in a list, first of all, I'm getting a couple pointers there for next and previous, so I have more memory. I have actually 24 bytes per node, but now I'm on the random axis. So according to this graph, I should be actually somewhere down there. That's just to populate the initial matrix stored as a vector or stored as a list. Well, the graphs are kind of, theoretical. Would it really be that bad? There's only one answer to this question. Well, yes, there is actually, it's always worse, trust me. Let's go see. The other one. So I have some data, and I'm going to push them back into 2 vectors, and all I'm doing, I'm actually copying from one vector to the other. So I'm just benchmarking reads and writes. I don't want to add multiplies, because they'll just dilute the cost of memory reads and writes. You can figure out, if you know your multiply takes 3 times as long as the read and writes, you can figure out what the average is. But I'm just going to measure reads and writes. I'm just copying the vectors back and forth. Same thing with the lists. I'm not actually reallocating nodes. So after I did the pushbacks on the lists, I'm just pulling the floats out of the list nodes, writing them into the other list node. In my initial allocation was done with pushbacks. After that, I'm just copying values from wherever they sit in memory. So there is no malloc calls in the benchmark portion after I'm done the pushbacks. So I'm not benchmarking malloc. What happened? Sorry. It's a problem. Okay, that's my, okay, it's compiled. Okay, now it's running. Vector. This is both read and write are involved, it's a copy. So it's slower than just writes. 6-ish gigabytes per second. List. Well, we're now in the world of herd. And I promised it's only going to get worse. Okay, so yeah, it's pretty bad. Now, at this point, you could say, okay, well, that's true, all of this is true, but in reality, it's actually much simpler than what you're saying. You take your existing program, you run the profiler, you find the toll pole, and you optimize it, you run the profiler again. That's easy. Whatever sticks out, hammer it down. You do that, and in real life, you end up with the case where nothing really sticks out, but nothing is all that great either. And what does it mean when you're in that life? So no single place in the program takes more than 2%, but overall it seems like your performance isn't what it could be. What does this tell you? Well, one thing it tells you, there isn't any one piece of code that you could optimize and be the hero of the month, but what else? Possibly. Yes, so there's definitely something about the design. More specifically, 9 times out of 10, if you don't have hot code, you have hot data. And that doesn't show up in the profiler normally, because it's peanut buttered across your entire code base. Everywhere where you're accessing this, not necessarily one data structure, but this volume of data organized in a certain way, you're paying this penalty for inefficient memory accesses, but it's scattered all over. If you're very lucky, it'll be one data structure, at least one type, and at least that accessor function, like list iterator access, would at least show up on the profiler. Now, you still can't optimize it because you can't write list iterator better. It's very difficult to improve list iterator. You could see where it's being called from. Well, it's being called from everywhere. So you still can't approach it as a code optimization problem, but at least you know which data structure it was. Still a data optimization problem, but the coding profiler would at least tell you what data it was. And that's actually one of the benefits of the good design, because by encapsulating our data structures, we could at least get from the normal code profiler the information about which data structure it is that is poorly, inefficiently accessed. The compiler will tell you every place where that function is called if you want to, but there still isn't a single place you could optimize, but at least you know what data has to be reorganized. And you really have only 2 options. You can access this data less, or you can organize it differently. Both of those are design concerns. They're not implementation concerns. So you design certain data model. You have accesses permitted by the data model enshrined in your design. It would take a redesign to change that. So one of the things the design determines is the data flow at a high level of your program. What are your components? Who knows what? How do they find out about the information that the other one knows? How is this information passed from one to the other? How can you ask for information? What do you ask for? How much do you get? In what order? Things like that. And that will limit your performance. You commit to a data organization, not necessarily data structure, data organization that permits random access, you're going to be looking at that until you redesign. Little things can limit you. I want a hash table. Here is a std map. Hash table, I can implement hash tables in a lot of different ways. Well, that particular one, in its API, has a bucket iterator API. Now I can't implement it in a lot of different ways. It has a list inside. And that's because it has that thing in its API. I'm not going to argue whether it's justified or not. I'm just saying you do something like this in your own API, you have committed to that implementation. This example is actually from a real design. We do this kind of thing all the time. I digest it into a very simple code, but I'm going to explain you what I have, what I'm going to do. I have records. Each record is a contiguous chunk of memory, but length varies. And I have edits. And edits may or may not apply to records. I have to look at the record, I have to look at the edits. Okay, this edit wants to change something in this record, this edit doesn't apply to this record. And the ones that need to be changed, I have to change them and replace the old records with the new ones. And then I have a next change, and I have to do this over and over again. That's what my program needs to do. The most straightforward way to design this is I want to have my records organized in a data structure that allows insertions in the middle of the sequence. List, maybe tree. Then what I'm going to do is take any record that I want to edit, apply the edit, delete the old one, insert the new one where it was. That just calls for a std list. Let's see. Have some old code there. Okay, in this case, my records will be strings, and my edits will be regular expressions. In a real program, that wasn't the case. Records were complex data structures, edits were design-related manipulations, doesn't matter. Read some memory, change some bits, write the memory back in. Here is my list. I'm going to put some records into the list. And then I'm going to run some number of iterations. I'm going to make some random strings. I'm going to create some regular expressions. And I'm going to check if the regular expression matches the string. If it doesn't, we're done. If it does, I'm going to apply the regular expression as an edit pattern and replace it with something else. Delete the old record and put the new record back in. That's what this code does. The details don't matter. It does what was on that slide. Okay. Oh, and what I'm going to do is I'm just going to print how long time it took to do a certain number of iterations, and I'm also going to print the fraction of what percentage of the records I actually edited. I had to check them all, but I didn't have to edit them all. So what percentage I actually edited? Okay. It took me however much work I generated in this case, 3.8 seconds, and almost every record was edited. Now, this is not the only design as far as the data organization. Can you suggest a different design for this? Just different design of data, yes?
Generate the whole list of edits so you don't have to walk the list.
Well, walking the list is actually very cheap. Suggestion was generate the whole list of edits. Walking the list of edits is very cheap. I have millions of records. I take one edit, apply it to the whole million of records, go to the next one. It takes me an hour to apply the set of edits, then I move to the next edit. No big deal in this case. I didn't mention this, but even in this test case, it takes me maybe 1/10 of a second to apply one edit, and then I go to the next one. So getting edits isn't really a problem. What else? Deck, okay. Sorry? Okay, vector. Let's start with a vector. Vector is a little simpler. Okay. So I'm going to put all my records contiguously in one array one long chunk of memory. Could be vector. I'm going to apply the edits, check the edits first. Now I have a problem. If the record doesn't need to be edited, it still has to move if I want to end up with another vector after I'm done. So I'm going to move it either way, which means I'm just copying the bits. I'm going to copy the bits whether I'm editing or not. So this is what the design looks like. Whether it needs to be edited or not, I'm going to copy something. If it's edited, I'm going to edit it on the fly. If it's not, I'm just going to copy the original one. And when I'm done, I'm going to delete the old chunk of memory, reallocate it. Well, I'm not going to actually delete it. I'm going to reuse it, but whatever. And do the same thing all over again. And keep doing it. Does consume twice as much memory at the peak usage, but never mind that for now. We can deal with that later. Okay, I didn't do vector. Wanted to make sure there are nothing funny going on, no reallocations. I just mallocked an array of memory. Otherwise, it doesn't, the same thing. So make random strings. Okay, here is the benchmark actually starts. Okay, if I need to edit, I'm going to apply the edit. Otherwise, I'm just going to memcopy the record. And it's just char star in my case. So I'm simplifying. It'll do the same amount of work. So you can actually see these are the record counts. So it did the exact same amount of work. Almost every record was edited, but it was 4 times faster. Now, you could say, well, of course it was. You edited every record. You didn't actually lose anything on those moves, right? Was that it? Is that the reason? Let's try. The longer my regular expression gets, the fewer random strings. So the longer, if my regular expression is like more characters, the less chances are that it'll apply. So if I do regular expression of 3 characters, there is much fewer records will be edited. That's the list. 5 seconds. 1.5% of records were edited this time. That's the vector. It took me exactly the same time now. But so the memory copies, the unnecessary memory copies, basically evened out the advantage I was getting from the better memory access, unless there is something else going on. That's where you have to profile this stuff. Actually, let me show you the difference. It'll be easier to see if I just show you the difference between these 2 versions of the code. That's the difference, the ones in red. On the left is the C++ regex. On the right is the old libc regex. In this case, I'm doing your basic expression, simplest regular expression. There is no pattern, just like replace these characters by those characters. So there is nothing fancy going on. Both C++ and C can do it. It's not an issue with the regex library. Same number of edits runs like almost 10 times faster. There's actually a reason for that. And it will come back all to the original point that I was making about the design and the memory, which is what I'm showing. So that's the good one, the fast one, that's the C. It's all in regular expressions. Let me do the other one. Okay, it's it's in here. It went into the regular expression stuff. It actually went into the allocators. I would have to make a bigger screen, but trust me, it allocates and deallocates a lot of memory in the process of doing this. And that's actually where the memory penalty, where the penalty is. So again, comes back to you have to be really careful with how you manage the memory in high-performance design. Allocating and deallocating a lot of memory is just as bad as reading the memory inefficiently. Now, speaking about reading the memory inefficiently, somebody said DEC. That's an improvement over our previous design, and the improvement is we actually don't have to consume twice as much memory at the peak. What can we do? We can take large but still contiguous blocks, and yeah, we'll suffer a random-ish access when we jump blocks, but that only happens once per n records. So we're going to be consecutive within one block and flow all the records from one block to the other. And then as soon as this block the old block is drained of records, we're going to reuse it. And maybe we need more than one block to, if the records grew during the edits, that's no problem. That extra advantage is the most recently used memory, the one we're going to be reusing, is the one we just freed. It's still hot in cache, we were just reading from it. These are very high-performing designs. If you can do it, good memory management strategy. But as a price of getting there, we had to restrict access to our data. In general, restricting access is one of the most powerful tools you can do in designing for performance. You can organize data for optimal performance access. You can reorganize. Between that and the high granularity APIs, these are really your most powerful tools in making sure your design isn't, if not high performing now, is amenable to high performance. Now, if you temporarily need to switch to a very different model of memory access, you may have to create a temporary data structure, index, searchable data structure, sortable data structure, and that'll have some cost. And you'll have to pay it from the budget you saved by not doing random access all over memory in the first place. But that budget is large. You can actually pay quite a lot. All of this has to be influenced by measurements. You can't make good decisions without good knowledge, and the good knowledge has to come from experiment. And measuring requires a working program. So how do you have a program to measure before you designed it? And the answer is, design for performance, again, may be unique in this way. You have to have prototypes, mocks, simulation pieces. You have to somehow estimate the rough idea of what it's going to cost you to do maybe the lower bound of the operations that you want to do on the data organization that you're contemplating. You have to measure it and put it into your consideration. How long would I need a gigabyte on disk? How long would it take you to read the gigabyte from disk? Well, now you know if that's unacceptable, your design with a disk-based memory isn't going to fly for performance. Things like that. But prototyping is critical for designing for performance. Yeah, let's skip that. Okay, I was going to show design for concurrency, but as I said, this will be another talk. Instead, I'm going to show you something else. Everybody's favorite, yeah? It's time to wake up now. This one is going to be really good. Undefined behavior. Using undefined behavior for fun and profit. Well, it's always for fun. I mean, you can do evil thing to somebody. But this one is actually going to be for profit too. Now, what I don't mean is the undefined behavior, I see Ansel here, there's Barbara here. I can screaming, please no, not that, just not that. Well, I don't mean that one. Don't do that. That may make your program really, really fast. Don't do it anyway. I mean undefined behavior in the context of the contracts your application gives to its clients. And now I have to give you a real example. Okay, yeah, 5 minutes, we'll make it. A lot of our work has to do with geometry analysis. The most primitive geometry type we have is a polygon. Everybody knows what the polygon is. But we have another interesting one, and it's called a constraint. And this constraint is also geometry. It's physical geometry, it's drawn. And the constraint looks like two lines. But it's the same object. It's one object, it just has two lines. Just like polygon looks like four vertices, or square looks like four vertices, but it's this, they're all together. It's not just four vertices. It's a unit of four vertices. Constraint is two lines. And the operation that I want to do is I want to create a graph where polygons are nodes, and each polygon has a number, so that part is easy. And the constraints will be edges. So now I'm saying the constraint must touch exactly two polygons. One on each side. I have two lines, so one on one line, one on the other line, and then I'll draw the edge in the graph. Okay, is that clear? Yeah, okay. So I have the code that does that, it's pretty straightforward, but then what happens if you have something like this? Nobody said this cannot happen. I'm allowed to draw any two lines and declare them one constraint. So what do I do? Well, you can't put it in the graph. Edges connect two nodes. There is no such thing as three-node edge, at least not in the kind of graph that we're building. Well, I can define what happens. I can decide what happens. I'm declaring it to be undefined behavior, which means I'm allowed to create one edge or no edges at all, or more than one. I can do whatever I want. Why did I do it? The answer is performance. I can actually save. Detecting this condition is very expensive compared to how efficient the implementation can be. As soon as I detected one polygon on the left side and one polygon on the right side, I created an edge in the graph and I threw out that constraint from any further consideration. If I don't do this, I have to keep track of it, and the lines could be long, and I have to make sure I have seen all polygons that could possibly interact with those lines all the way up there before I dispatch with this constraint. Very expensive. So I intentionally defined for myself a narrow contract. If you are in contract, each constraint touches two polygons. I'm going to give you something very fast. If you're out of contract, you're in UB land. So this is the way to think about it. It's really not so much UB. It's a very narrow contract. Correct behavior is guaranteed within the contract, because that behavior can be implemented much faster than anything else. If you do this, please, good design calls for one more thing. Provide a way to detect that this happens. It doesn't have to be fast. It's a debugging tool. It's a debugging tool for your users. We have it. It runs 10 times slower, but we can actually report every constraint that was causing UB in the original problem. So, one more thing, so I wanted to add, repeat it. The most important thing, you design for performance. Performance has to be factored in from the very beginning, and it has to be influenced by good knowledge, by measurements. The way you organize data is going to be the most important aspect of how you design influence your performance. You should be not restrictive with your APIs. You should give yourself as much freedom to implement as possible to allow for changes that improve performance. In particular, perform as high granularity requests as possible. You will have to write exotic code. Please contain it in a dark, narrow corner of your program. It has to be fast. It doesn't have to be in my face all the time. Good design practices combined with all of those principles that I'm telling you will help you make your designs maintainable, optimizable, rewritable, refactorable, all of this good stuff, combined with those other things. Good design practices written with disregard of the good knowledge about performance may lock you in a bad performance. And if you have a big difference between a narrow contract and the wide one, and you only need a narrow contract, do it. Just provide the debugging way. Don't hesitate to take advantage of a narrow contract if it makes a difference. Thank you, and credit to my sister-in-law who did the cartoons. I'm not as We can have a few questions, but I'll be here the rest of the day, and I'm happy to talk to you and show you the code and run the profiler and show you the assembly instructions and everything. Please. Questions?
Sorry about that. Yeah. I'm thinking of the early days of OpenGL where initially the thought was you would push some vertices and then do some operations. Basically, I'm wondering if you've ever, and it didn't work out. They ended up redesigning OpenGL to send things in batches. Have you ever run into a case where actually interleaving computation and memory access in that way was actually better for performance, or is it pretty much, because it always seems to me like it's better to work in large batches. I don't know if I'm making sense or
Okay, yeah, you do. Okay, so it's better, it's possible, especially with the vectorized stuff or multi-threaded stuff, that interleaving memory accesses and computations can give you high performance, in particular pipelined architectures where you have multiple threads handing over partially computed data through a pipeline. Those can be incredibly fast. It's almost never going to be the way you constructed that incremental narrow API. It's not going to match the best pipeline or the best whatever. So yes, you could gain by interleaving memory accesses with computations. The odds of you guessing the right way when designing a small granularity API are practically zero. So you still want to have a high granularity API, and the implementation may end up processing data in small chunks.
okay.
Just
Thank
not the way you were originally planning.
you. Okay, thanks.
These were excellent examples.
Thank you.
By necessity, because of the format, relatively small in scope. I'm wondering, in your experience, how have the techniques that you're describing, or how do they need to change, or if they need to change when you're dealing with kind of software that most of us deal with on a daily basis? So very large systems composed of many interdependent components.
Okay, so this was obviously condensed to what I could fit on this laptop and on one screen. The real like that thing with the memory blocks and the records flowing across takes like 0.5 terabyte of memory on a large system and runs for 12 hours, doing basically just that fundamentally. So it scales. A lot of these actually scale much better because pretty much everything, what I was talking about, will get more expensive with scale. Memory accesses, I've shown you the difference was about 100x between the best and the worst. On a large system with like 64 CPUs and 1.5 terabytes of memory, it'll be even worse than that once you get to the full production sizes. So most of these things actually get worse. It's a challenge on your design because your designs also become bigger, so multi-level components, smaller components, bigger components, so kind of nested separation of concern things. So it's a challenge on the design. In this regard, it gets more complex. But so you may have to, how do you eat an elephant? Well, one bite at a time. So you divide your system in large components, each component in smaller components. That's how you tackle it. So you have to tackle that complexity. But as far as the principles, at every level, you basically figure out how much complexity you can handle. You design that many components, that much of an API, but you have to use these considerations, like at every level of your hierarchical descent from the nice, highly organized design into the madness of vectorized instructions all the way down. Well, if there are any more questions, just come and see me and talk to me. And as I said, we can look at the code. I'm happy to talk to you. Thank you again.